We're going to jump into another chapter. This is for exam 3. Yep, chapter 8. And this is the only chapter in exam 3. Don't let that fool you though, because we're building on what you've learned in chapters 1 through 4. So if you're not fully confident with the chemical symbols and naming compounds, then you need to continue to work on those because they're going to be critical to understanding the material from now on. All right, chemical composition, and we'll get to those other chapters in subsequent exams. Chemical composition. All right, like I said before, we've learned the alphabet, which is symbols for the elements. We've learned how to put those symbols into words or compounds, and how to write the compounds, how to name the compounds, and how to swap back and forth between the two. We've learned that naming conventions require that the name be unambiguous and non-redundant. And that's going to be critically important for doing what we're proposing today. Because if you have a name that can designate 2 or more different compounds, then all you have is a mess. You need to be able to identify each compound by its name and write the compound formula so that we can continue with what we're going to study today. All right. At the very beginning of the semester, I encourage you to consider chemistry on the microscopic level. We can observe things about the natural world, but if you don't make the connection, and this is actually intuition, an intuitive connection between what we observe and what's actually happening underneath at the microscopic level, then you're missing out on a skill that will allow you to proceed with the least amount of pain and effort with chemical reactions. So this is one way that we bridge the gap between what we can see, what we can measure, and what's happening underneath. And in order to do that, we need to be able to determine the masses of individual atoms, or at the very least, the masses of known numbers of atoms. Now, we don't have the ability, most of us don't have the ability to count individual atoms. That requires some very expensive, very technically complex equipment. And it's very tedious, and it doesn't add to our understanding from a chemical reaction standpoint. Well, I say it doesn't add to our understanding. It does add something, but it's not accessible to most chemists. So what we need is a way to use our macroscopic tools to get a handle on the microscopic. And that's what we mean by counting by weighing. We can go into almost any lab and find a balance. And if we have what we consider a pure element, naturally occurring element, then we can put that element on the balance and determine its mass. We need the bridge between that mass and how many atoms we're actually talking about when we weigh the mass of that element. Okay, okay, so here's what we mean. say we have a jar of marbles. Just assume that that whole jar is full of marbles. We want to know, within reasonable experimental error, how many marbles are in that jar. But that jar is huge, right? I drew it small here, but I'm telling you the jar is as big as a boxcar. In order to count the number would be very tedious and prone to larger errors than we could by other methods. The other method I'm talking about is actually weighing that boxcar of marbles. Now we have balances that are big enough. We can weigh that whole boxcar. If we know what the mass of the boxcar is, and we know the total mass, then we can subtract that and find out the mass of the marbles, okay? But the bridge is the average mass of a marble. So we take out a subsample and we find its mass. Okay, so let's say we take out 100 marbles. So for 100 marbles, let's say they're 200 grams. Okay, that means that each marble is 2 grams per marble. Okay, now we've got a conversion factor. We can go from numbers, we can go from mass to numbers. So let's say we weigh that boxcar and it weighs 12,000 kilograms. It's a big boxcar. 12,000 kilograms. Well, we know from experience and dimensional analysis that we've studied in the past that we need to convert that to grams so we can use this conversion factor, right? So we need to go kilograms, grams, which is 1,000, right? Now we can convert grams to numbers of marbles. We got 2 grams per marble. Okay? This is a 3, there we go. So that 1,000 would be 12 million grams. And then we divide that by 2. And we get 6. We get 6 million marbles. And that was a whole lot quicker, taking out a sample of 100 marbles. It's a lot quicker, a lot easier than trying to count the whole boxcar. This is a similar problem that we face with atoms. If we think of atoms instead of marbles, then instead of counting all the atoms, we want to take out a few of them that we can count, and how much does that number weigh? Then we can use that with the total mass of our element to determine how many atoms are actually in that container. All right. So our example here is jelly beans. So let's say, what's the mass of 1,000 jelly beans? Well, not all jelly beans have the same mass, right? We just assumed in this case that all the marbles have the same mass, but even then they probably don't. There's some variability. What we need is an average mass. What's the average mass of jelly beans? So we take out 10, right? And there are the results that we get from putting each jelly bean on the balance. Then we take an average, right? So the average jelly bean weighs 5 grams. Now that may or may not be the mass of any one jelly bean. In our case here, we have 1, 2, 3, 4 jelly beans that are 5. We have others that are more than 5 and some that are less than 5. So our average mass is 5 grams for each jelly bean. Now we know that if we multiply 5 grams times 1,000 jelly beans, we have 5 kilograms. Excuse me, we have 5,000. No, back up. There we go. 10 jelly beans is 50, so that's 5 grams per jelly bean. Oh, we could find the mass of all those jelly beans, just say 5 times 1,000, so it would be 5 kilograms. I guess this exercise is just to familiarize you with the process of finding the average mass of a particle of some kind, a jelly bean, a marble, an atom. Okay, the object of this statement. Let's make some room here. And clean up some of the ghosting. Say we have 2 samples of different types of components. Right? We have a sample here of A's. And we have a sample here of B's. Oops. Didn't mean to do that. B's. Okay. So for argument's sake, we have 4 A's in this container and 4 B's in that container. That means they have the same number of particles. But they're different masses. We've got a mass of A's and a mass of B's. And let's say for argument's sake, the mass of B is greater than the mass of A. Okay. So not including the container, right? We subtracted the container mass. So this is just the mass of the B's. If that's the case, if this total mass is greater than that total mass, why is it that different? Because each one of these components weighs more than each one of these components. The ratio of the total is equal to the ratio of the individual. So the total, let's see, total mass here, the ratio of that total mass to the total of the mass of A is equal to, by ratio, the mass of a single. Okay? The ratio is the same for both of them. Because the only way that this one can be greater than that one is because each one of these is greater than each one of those. All right, so let's see. We don't need to spend a whole lot of time on this one. We just have a pile of marbles that weighs 394.8 grams. 10 marbles weighs 37.6 grams, which means, and the question is, how many marbles are in the pile? Well, we can calculate the individual average mass of an individual marble. That would be 3.760 grams, right? 3.76 grams per marble. Then if we divide by, and we left out some components here, this is 3.76 grams per marble. So the grams cancel and leaves us with marbles. Okay. That's what we mean by when we say counting by weighing. Because the mass is not going to change and the numbers won't change. Right? As long as we're not close to a black hole or traveling at the speed of light, then the mass is not going to be different. So those are stable quantities. Now, when we consider counting by weighing, not marbles anymore, because we're really interested in counting atoms by weighing. But atoms have a very tiny mass. So scientists came up with a unit for these small masses called the atomic mass unit. Now, in terms of grams, one atomic mass unit is about 10 to the minus 24th grams. So it's very small, but it's easier to handle when we're talking about individual atoms. Okay. Now we also have to consider, and I think we've covered this in the past. Let me just check myself. I don't want to introduce a topic that we haven't already covered. Yes, we have. We've covered isotopes. So the average atomic mass of an element is a weighted average of the masses of all the isotopes of an element, which means if you have, say, carbon can occur in 3 isotopes that are significant. We can have 12, we can have 13. These are stable. That is, they don't decay, radioactively decay. This one does radioactively decay. That's the one we use for carbon dating. But if this one is, for argument's sake, let's say it's 98%. That means this one is a little bit less than 2%. The weighted average is impacted more by this isotope than by that one. That's what we mean by weighted average. It's kind of like determining, calculating your grade point average. Right? If you take a course that will give you 4 credit hours like this one, and you make an A in this one, then that has a greater impact than if you take, say, a lab course with only 1 credit hour and you make an A in that one, or you make a B in that one. The average is weighted more heavily toward the 4 credit hour course. Right. So what we need is a standard that we can fix, and everybody agrees what the value is. If we can come up with that value, then we can relate, and I'm saying that value for an individual isotope. Then we can relate all the isotopes of that element to that one, and eventually we can relate all the isotopes of every other element to that one. That's our standard. Now, our standard happens to be carbon. Right? That carbon isotope is given and fixed at this value. Twelve atomic mass units for that isotope. And that's by international agreement. So it has infinite significant figures. But that's not the only. If we were to take a sample of carbon, say we were to take some living matter, like a chunk of wood, and we were to pyrolyze it. That is, we were to heat it up hot enough with no oxygen so that everything breaks down, but it doesn't combine with oxygen. In other words, we're breaking the elements apart by heating them. So now we have a mixture of a number of elements. Some of those elements we can evolve as gases and get rid of them. Some are ash, and we can dissolve them in certain types of acids and get rid of those. Eventually, we can purify that to have nothing but carbon. That's what we consider naturally occurring carbon in the environment, and it will have a ratio of various isotopes. Most of them will be this one, but there will be a significant number of carbon-13 isotopes. So what's the mass of an individual carbon-13? It will not be 13. This is the only one that's fixed at infinite zeros. This one will be 13 point something probably. And when we take the relative percent of each one of these and we weight the average, we will come up with a value of 12.01 atomic mass units per atom. Now, let's see. I want to make one other statement. What's the probability? Probability of a single atom with 12 atomic mass units as its mass. Let's make it a question. What is the probability of a single atom with 12 atomic mass units? Okay. Remember, this is a weighted average value. The probability is 0. Zero % probability that any one atom will have 12.01 atomic mass units as its mass, because this is a weighted average. This is not an individual. The example we had earlier with the marbles, we don't want to carry that analogy too far, because some of those marbles had the same weight as the average, but in nature, there are no atoms for any of the elements that have the weighted average atomic mass units for that element as their mass. Weighted average means it's an average of all the naturally occurring isotopes. So there's not a single element that has the exact value of 12.01 for carbon, or for instance, 35.45 atomic mass units for chlorine. Doesn't exist. It's a calculated value, and it's a calculated value to help us, because if we know that value, then we don't have to be concerned with whether we're conducting a reaction with this isotope or that isotope or this other isotope. We just take that, they're a jumbled average, and we go from there. All right. Calculate the mass in atomic mass units of 431 atoms of carbon. 431 atoms of carbon. This is a dimensional analysis problem. You just need a conversion factor. And we just gave you the conversion factor. We want to go from atoms, right? Denominator, numerator, those cancel, to mass, right? So we actually only have one. 12.01 grams per atom. So we multiply 12.01 times 431, and we get a value, right? 5,176 atomic mass units. For that many atoms. Let's do it for aluminum. How about that? We just change these values to aluminum. How many? 75. 75 atoms of aluminum. What's the weighted average for an aluminum atom? We have to look on the periodic table. If we look at the periodic table, we find a value. We find two prominent values. The first one is a whole number, which is the atomic number, the number of protons in each atom of aluminum. That's a fixed number. And the other number we find is the atomic weight. For aluminum, it's 26.98. Oops. That was a mistake. Atomic mass units per atom. So when I said grams per atom, that was a mistake. So 75 times 26.98 gives us 2,000. Right? So on the previous problem, we had 5,000, but we had 400, over 400 atoms of carbon required to give us double the mass of just 75 aluminums. Why the difference? Because aluminum is more than twice the mass of each carbon atom. All right. Now, the atomic mass unit is a good place to start to understand what we mean by weighted average, what we mean by isotope masses, what we mean by the mass units on average for carbon. In this case, carbon, 12.01 grams, 12.01 atomic mass units for carbon. Okay, 12.01 atomic mass units per atom. This is for carbon. Okay. What we have done is we've measured and chosen a value called the mole. If we have a mole, and a mole is a counting number, it's just a very large number, so we can count a lot of atoms, enough so that when we put that many atoms on our balance, we have a measurable quantity, right? We don't have a balance that will measure this small a value. So we have a mole. If we have a mole of atoms, then we will have exactly 12.01 grams. Okay, so these values are interchangeable. They're different units, but the values are the same. This is more useful. Now, 1 mole happens to be, this is the full name, this is the abbreviated name. Now, it could be atoms. It could be molecules. It could be ions, right? It's just a number. Now, it's based upon reality. It's a measured number. But once we have the number, it could be anything we want it to be, right? It could be a mole of electrons. It could be a mole of protons. It could be a mole of chickens. It's still a number. All right. And since it's a ratio, this can serve as a conversion factor. For instance, if we know the number of moles of carbon, we can use this to tell us the number of grams. If we weigh a sample of carbon and we get a certain mass, we can use this value to tell us how many moles. And since we have a value associated with moles, we can also determine exactly how many atoms are in that sample. All right. So this chart tells us that for each of these elements, if we have exactly the same number, 1 mole of each of these elements, we have a value. The aluminum we just did, I erased it, 26.98 grams. If we have a mole of gold atoms, that will be the same number of atoms as aluminum, but the total mass will be 196.97 grams. Why is that? Because each gold atom is more massive than the aluminum atom. That's why the same number of atoms gives you a different mass. Those are just examples. You can find any one of these in the periodic table. You just need to know where to look for them. That's why I gave you guys that extra credit exercise to fill out the periodic table to help you learn where things are located. If you took advantage of it, then so much the better. All right. So determine the number of copper atoms in a 63.55 gram sample of copper. All right. So we're going to need, what's the question? The number of copper atoms in that mass of sample. Do we have all the information we need right here? No. You have to go to the periodic table. 63.55 grams of copper. And in order to determine the number of atoms, we have to bridge the gap between mass and numbers. And the bridge is always molar mass. In other words, grams per mole. So we go to our periodic table and look up copper, and it's 63.55. That means this divided by that is 1. We have 1 mole, which is equal to 6.022 times 10 to the 23rd atoms of copper. Okay. All right. This is actually, the more I look at this slide, the dumber it becomes. When we say 1 mole, it takes that many atoms to equal over 60 grams. So if we're talking about one atom cannot weigh 63.55 grams. It can't weigh 52, it can't weigh 58, it can't weigh 65. So the only possible answer is E. that very small value. And you can do the calculations right there. It's a multi-step conversion that gives you the exact value for the mass of one atom of copper in the unit of grams. Okay. What if we have calculate the number of iron atoms in 4.48 mole sample of iron? Now, let's see. We have, okay, it's not multiple choice. If we have that many atoms of any element, and we know we have 4.48 moles, then we can calculate the number of those, and it doesn't have to be iron. It can be anything. Once we got to the point of counting, then it doesn't matter what the element is. If you want to answer that question, you only need Avogadro's number. That's what 6.022 times 10 to the 23rd, that value is given Avogadro's number in honor of the scientist, Avogadro. So there you have 2.7 times 10 to the 24th atoms of any element, in this case, iron. Okay. A sample of 26.98 grams of aluminum has the same number of atoms as how many grams of gold? Well, we know that 26.98 grams of aluminum, we've looked it up, and that is 1 mole. That's 1 mole of aluminum. So 1 mole of gold, we just look it up, and it's 196, or rounded off, 197. So C is your answer. Okay. There it is. Gold atoms are heavier than aluminum atoms. So if we have the same number, then the total mass of gold is going to be much higher than it is for aluminum. All right. So let's work this one on the board. We have a 100-gram sample of each one of these elements: magnesium, zinc, and silver. Okay. This is where I'm going to invoke Henry Ford. Set up an assembly line. We have 100 grams of each one. Now, if we want to do the calculation and determine the greatest number of atoms, then we can do that. But if this question comes up on a test, you want to get the answer quicker. If they have the same mass and each atom or each mole of atom silver is going to be 107.87. Zinc is going to be 65.38. Magnesium is going to be 24.31. Okay. So what that tells us is silver is the heaviest atom. And magnesium is the lightest atom. So what that means as a practical matter is that the lighter, if you need 100 grams of each one, which one takes the most number of atoms? The lightest atom does. It takes a whole lot more magnesium atoms than it does silver atoms to make 100 grams. So we could calculate it, but we can answer the question right there. Okay. We know magnesium is going to have the greatest number of atoms because they're all the same mass. Now, this one is a little more complicated. Let's see. Let's start over and put them in the same order as on the slide. They're the same elements. They're just in different orders. So let's say 107.9 grams of silver. Silver, 107.9 grams. And zinc is 70 grams. And 21 grams for magnesium. Okay. Those are different sample sizes. We want to rank them in order of the greatest to the least number of atoms. Well, if we do the conversion, using their molar masses, then magnesium is going to be 24.31. 24.31. Zinc is going to be 65.38. And silver is going to be 107.87. Okay. If we're just ranking them, we could do the calculations for sure and rank them. But if we're in a hurry and all we have to do is go from greatest to least number, we would say, all right, what do we have here? 107 divided by 107, that's equal to 1 mole within experimental error. This one is greater than a mole, right? That's smaller than this one, so it's going to be greater than 1. This one is going to be less than a mole. Okay. Now we know from greatest to least, we have zinc, we have silver, and then we have manganese. So that's our order. Now in the slide, I actually calculated it, but either way works. All right. B is zinc, A is silver, and C is magnesium. All right, this is just, we digress for a moment. When you try to solve a problem, what the authors mean by where are we going is, what's the question? What's the final destination? What will our answer look like? So you have to read the whole problem and see what the final answer is going to be. Some problems are very simple. So when you devise a method for solving that problem, it could be simple. It could be one step, right? Or it could be multiple steps. You have to break the problem apart into pieces and get an answer for each one of the pieces before you can put them together and produce your final answer. And then your last step is, does your answer make sense? I had a friend, I was in graduate school at LSU in Baton Rouge. I was working on my PhD, in agronomy, crops and soils. And he was my neighbor in the apartment complex, and he was working on his bachelor's degree in mechanical engineering. And he would tell me stories of some students in their classes who would come in to take an exam or a quiz, and they would be so stricken with tunnel vision from the chapter that they had been studying in their textbook that they would take the values given in the problem and force a square peg into a round hole in the formulas that were available from that chapter. and they would come up with some wild answers. And they couldn't understand why, because they didn't do the reality check. When you're working on a compound bow design, which my neighbor was doing that, and you want to know what's the let off. In other words, maximum force to minimum force when you hold it back for a compound bow. What's the let off? It could be something like 50 or 60 pounds. Let's just say that's it. Right, 50 pounds of let off. And these students would use the formulas that they had gleaned from that chapter and put in their values, and they come up with something like, you know, 1,000,000 pounds. And it didn't dawn on them, or they had no way of figuring out why they got the wrong answer. So it's very important that you do a reality check. Does your answer make sense? One of the ways that I use to determine if an answer makes sense is, once I've set up the problem, I go through and estimate the answer. And you can do that really quickly. If you practice it for a while, you get good at estimating that, or you say, does this answer make sense in the real world? Right? You may do a calculation, find out the moon weighs 27.5 grams. That makes no sense whatsoever. You're talking about billions of grams for the moon. All right. So that's what I mean by reality check. Does it make sense? If it doesn't make sense, you ought to at least check your math. Okay. This value we call molar mass. How much does a mole of any substance weigh? We can count the number of particles. In the case of an element like nitrogen, we count 6.022 times 10 to the 23rd atoms of naturally occurring nitrogen. So we'll get a mixture of the isotopes. And that many will put them on our balance, and we should get 14.01 grams. That's the molar mass of nitrogen. What do you do if you have a compound, though? Well, if you have a compound of, say, water, and you have 1 mole of water molecules, 6.022 times 10 to the 23rd molecules of water. Well, how many atoms of oxygen do you have? That represents 1 mole of oxygen atoms. But it represents 2 moles of hydrogen atoms, right? So for 1 mole of that compound, you get a mole of hydrogen atoms, oxygen atoms, and 2 moles of hydrogen atoms. So if we have 1 mole of oxygen atoms, that mole of oxygen atoms weighs 16 grams. But 2 moles of hydrogen atoms equals 2 times 1.01 grams, or 2.02 grams. Then you add these two together, and you get 18.02 grams of water per mole. That's how you determine the molar mass of a compound. You just add up the molar masses of each of the atoms times how many moles of each one you have. This one's a bigger one, barium nitrate. And you should be able to name that compound just that quick. Barium nitrate. It's a type 1 compound. Barium is an alkaline earth, so it only has a +2 charge. You don't have to say barium 2. That would be redundant. Barium nitrate. Nitrate is a polyatomic ion. So that barium nitrate, to determine its molar mass, we take the formula, and this just illustrates the fact that you need to know how to write these compounds. If I say, what's the molar mass of barium nitrate? You need to write this compound, right? 2 plus, 1 minus. That means we need 2 of them. There's your compound. If you cannot write that, then you cannot answer this question. What's the molar mass? Barium is 137.33 grams per mole. Right? We only got 1 of them. We have 2 nitrogens at 14.01 times 2. And then we have 6 oxygens at 16 grams each times 6. Okay. We get those values, add them up, and you should get 261.35 grams per mole of compound. All right. This slide, I think, is correct, but I think it adds complexity to the matter. If you want to know the moles of a compound, you take the mass and divide by its molar mass. All right, that cancels the grams. If you want to know the mass, you take the moles of the sample times the molar mass of the compound, and you get an answer. Dimensional analysis, though, is a more adaptable process. If you know the units where you're starting, you know the units where you want to end, then you need conversion factors in between. 1, maybe more, to get where you're going. All right. So here's another example. And we're only given the name. Notice that nickel has a Roman numeral behind it, 2. That means it's a type 2 compound. Nickel 2 carbonate. So we know we have nickel with a 2 plus charge. And we have carbonate with a 2 minus charge. How do I know that? I could look it up. Look it up in the table that's given to you. Right? Polyatomic ions. The carbonate ion is a 2 minus charge. Well, these charges balance. So this is the formula for our compound. Now we just go look for molar mass for nickel, carbon, and oxygen. 1 times nickel, 1 times carbon, and 3 times oxygen, and add them together. Right? And that gives us 118.7 grams per mole. All right. All right, this one is more complicated. We'll work this one out on the board. I think we got time. Let me see. Here. Yeah. We're about halfway through and we've got another hour. All right. If we have equal mole samples of dinitrogen monoxide, aluminum nitrate, and potassium cyanide, the question is, rank them in least to most number of nitrogen atoms in each of these samples. If we have equal mole samples of N2O and aluminum Nitrate, yes. And potassium cyanide. If we have equal mole amounts, then we can pick, right? We could have 1 mole, 2 mole, 3 moles. Let's make it easy. Let's just say we have 1 mole of each. That's equal moles. Okay. How many moles of nitrogen are in that first one? This one is 2 moles of nitrogen. This one is 3 moles of nitrogen. This is 1 mole of nitrogen. Okay. So when we rank them least to most, we would have potassium cyanide is less than dinitrogen monoxide, and that's less than aluminum nitrate. Okay. There you go. Now, suppose we have 100-gram samples of each one of these compounds. We want to rank them from greatest to least number of oxygen atoms, right? The previous example gave us moles. This example gives us grams. So in order to go to numbers of oxygen, we must make the conversion to moles or numbers of molecules. Then we can go to numbers of oxygen atoms. This is a multi-step problem. You have to recognize that we can't answer the problem directly from grams. We have to go to counting moles first. So again, I need the help of Henry Ford, the assembly line. So we got water. We got laughing gas, dinitrogen monoxide. We have CH362. That's probably propionic acid and CO2. Okay. And we have 100-gram samples of each one. Okay. Now, where do we go from here? We need to convert these masses of compound to moles of compound. Right? Grams in the numerator, grams in the denominator. Moles in the numerator. So how much does 1 mole of each one of these weigh? Well, we just did water. Water is 18.02. Dinitrogen monoxide. So that's 2 times 14.01 for nitrogens, and then 1 times 16 for the oxygen. And the slide is probably animated, but I think this is more instructive. 14.01 times 2, 2802, and then 16 plus. That's 4402. So this molecule, a mole of dinitrogen monoxide is 44.02 grams. This one needs 3 carbons, 6 hydrogens, and you look these up in the periodic table, and 2 oxygens. So 12.01 times 3, and then 6.06, and then 32. That's 7409. Okay. And then carbon dioxide, the type 3 compound, with 12.01 for the carbon and 2 times 16 for the oxygen. Right? That's 4401. All right. Now, this gives us moles of compound. All right. We could go through there and do this calculation and then go from there to oxygen. But I'm going to do it in one step. Dimensional analysis says we need let's see. Leave a space open here. This is moles of oxygen. Okay. Now, what's the ratio? For every mole of compound, how many moles of oxygen are in that? There's 1 mole of water, which represents 1 mole of oxygen. Same thing for this one. 1 mole of dinitrogen monoxide gives you 1 mole of oxygen. 1 mole of this compound gives you 2 moles of oxygen. And the same for this one, 2 moles of oxygen. Go. So we cancel grams with this conversion factor. Now this conversion factor cancels moles of compound and gives us moles of oxygen. So all we have to do is run the calculation. 18.02 divided times 1 is 5.55. And then 44.02 divided times 1 is 2.27. And this one is 74.09 and times 2 is 2.70. Rounded off. And then the last one, 44.01 times 2. Let's see, I want to do that one again. There we go, 454. Okay. So we're ordered from greatest to least number. Greatest number is this one. That's number 1. Next one, this compound, and this compound, in that order. Now, notice that the animation that I produced for this slide, I went all the way to the number of atoms. But if you're just going to rank them in order of numbers, the mole is just as good a value for numbers as actual numbers. So that's why I stopped here, and I should get the same answer. Water first, right? Carbon dioxide second. Propionic acid third, and nitrous oxide, laughing gas, last. I got the same answer, and I saved myself the trouble of an additional calculation. Okay. So let's clear the board. Let's see. Let me check something. All right, here's what I'm going to do. Because I got a subsequent slide coming up that's going to need, not letting me do it. Okay. All right. Okay, I can still see that. Water, nitrous oxide, propionic acid, and carbon dioxide. Molar masses. I abbreviate those molecular weight. That's old school. That's a molar mass. This is 18.02 grams per mole. This is 44.02. I want to preserve these values because we're going to need them in a subsequent slide. And then 44.01 mole. Okay, now we can erase the rest of it. Okay. We'll save that till later. Now we're going to talk about how many grams of fluorine are contained in one molecule of boron trifluoride. So we've got one molecule of boron trifluoride, which is what? Boron trifluoride. Okay. How many grams of fluorine are contained in one molecule? Well, if this is one molecule, we need a conversion that will go to moles. You know what? We don't have to go that route. One molecule of boron trifluoride has 3 atoms of fluorine. Right? So how many grams of fluorine is it? Well, we know we're going to have 3 atoms of fluorine in one molecule. So we can go directly to 6.022 times 10 to the 23rd atoms per mole of fluorine. And then we can convert moles of fluorine to grams of fluorine. And look it up on the periodic table, rounded to 2 decimal points is 19.00. There we go. Now all we have to do is, that's the thinking part. The rest is crunching numbers. 3 times 19 divided by Avogadro's number will give you a value of 9.465 times 10 to the 23. That's how much fluorine is in one molecule of boron trifluoride. There we go. All right. Now, I'm going to introduce a method whereby bench chemists have determined the composition of a compound in the lab. And they might use different methods to get there depending on what they find in their preliminary investigation. They find out what elements are contained. And then they'll design an analytical procedure to determine the mass of each one of those elements in that compound and relate those masses back to the total mass of the sample. Okay, and they'll express that as percent composition by mass. Right? Mass percent simply is the mass of an element in a compound divided by the mass of the compound. Okay, so in this case, we're saying that mass, actually percent by mass. Very often what you get a value, X percent, and we'll say mass. The reason we write it that way is percent means parts per 100. Now those parts could be volume per volume, mass per volume, volume per mass, mass per mass. In this case, it's mass per mass. It's grams per 100 grams. That's what that value means when we're saying percent is mass percent. So that's the problem with percent. You need to know the origin of the values. Are they mass, are they volume, or a mixture? Now, the bench chemist will do this, and they won't even know what the compound is. But we can also go the other direction. If we know the formula for the compound, we can calculate the mass percent of each element in that formula. And our example is iron 3 oxide. Iron 3 oxide. Right? So bring the 2 over here and the 3 over here, and there's your compound. That's why it's written that way. Okay. Now, in order to determine the mass percent, we have to fix a relative amount. So usually what we do is say 1 mole. So if we say 1 mole of this compound, then what's its total mass? The mass of a mole. So we add up the masses of iron. Iron is 5585 grams per mole. And 3 oxygens. That's the total. How much of that is actually iron? Well, 2 times 5585. Notice we've got iron in both of them because iron is separate here. That's our target. And here it's in the total. And then we say times 100. And I'm going to let the animation work it out for us. 69.94%. Iron. In that formula. Now, since there's only iron and oxygen in that formula, how much is oxygen? Well, it'd be 100 minus that, wouldn't it? It'd be 6, 0, 0, and this is 3. Right? It'd be 10, and carry the 1, 10, carry the 1, 10. So it'd be 30% oxygen by difference. Okay. Here's another example. Morphine, derived from the opium plant, has this formula, C17H19NO3. What percent by mass is the carbon in this compound? So I'll set it up for you. We have 17 carbons. So 17 carbons. We also have 17 carbons in the denominator. and we have 19 hydrogens. And we have 1 nitrogen. And then we have 3 oxygens. Times 100. So that's set it up. If you crunch the numbers, then you should get 71.6% carbon. 0.6% carbon, mass. Okay. Okay. Now here is the problem that I need those values to satisfy. If we have 100 gram samples of each of the following, rank them from highest to lowest percent oxygen by mass. Right. Ask yourself this question. Based upon the calculations we just performed with the previous examples, do we need to know a 100 gram sample? All we need to know is that you have exactly the same mass of each one. So I guess we do need to know 100 grams. All right. Think of it this way. Percent oxygen by mass is parts per 100. Grams of oxygen per 100 grams of the sample. Right? If that's the case, then all we need to know is percent oxygen, because percent is grams per 100 grams. Okay, I'm going to let the animation do this one. The fact that we have 100 grams of each sample means that whatever percent we calculate from the formula is the answer to the question. We just calculated the percent oxygen in each one of those compounds, and now we just need to rank them. Water has the greatest percent of oxygen by mass, followed by carbon dioxide, followed by propionic acid, followed by nitrogen, dinitrogen monoxide. Okay? Now, if we had been given, say, different masses for each one, actually, it wouldn't matter, because percent oxygen is prorated to 100 grams no matter what you do. Right? So the 100 gram part of it is irrelevant. Okay. Now that we know to go from formulas to percent composition, we're going to go the other direction. We're going to go percent composition to formulas. That's the more useful means. Okay. But first we have to understand what's meant by empirical formula versus molecular formula, or empirical formula versus, molecular formula. The empirical formula is, for a compound, is the simplest whole number ratio of atoms present in the compound. For instance, the empirical formula of water is 2 to 1. Right? We can't simplify it any further. But benzene, that's benzene. The simplest whole number ratio for benzene is CH. How about acetylene? Here's acetylene. It's also CH. Okay. So the empirical formula is usually not the end game. It's a point on the way to the final answer. notice that if we put a 6 here and a 2 here, and then multiply each one of those by that one, we get these formulas. So that subscript propagated through the empirical formula will give us the molecular formula. That's our target. We want to know what that integer is. And it has to be a whole number. All right, here's an example. Let's do this example. Remember, when we're doing the empirical formula, we want the ratio of numbers of atoms. Okay, so if we have mass, we have to find a way to go from mass to numbers. A gaseous compound contains carbon and hydrogen. Okay, we have carbon and hydrogen only in that compound. And the was found to consist of 83.65% carbon by mass. 83.65% carbon by mass. How much hydrogen? Well, it's the difference. Right? 5, 3, 2, and no, that's not right. Um, 5, 6 from 9 is 3, that's right. 3 from 9 is 6, there we go. And 8 from 9 is 1. There we go. So now we have the percent composition of hydrogen. We can check ourselves, right? Add it together, right? Carry the 1, carry the 1, carry the 1, 8, 9, 10. So that's 100%. Okay. What do we know? How do we know? Can we go from mass to moles? Yes, if we know the molar mass, right? But that's not mass. That's a ratio of masses. So in order to simplify it, in order to get us a number that we can deal with, we say, what does that mean? That's 83.65 grams per 100 gram sample. Right? So let's just assume that we have a 100 gram sample. Now, with a 100 gram sample, we know that they're 83.65 grams and 16.35 grams of each of those elements. Now we can change them to moles. And for hydrogen, it's 1.01. And for carbon, it's 12.01. Yeah. So we're going to get, and remember, the law of definite proportions says that the ratio of masses of elements in a compound is fixed for that compound. So this ratio is the same no matter where we get that compound. It doesn't matter where it comes from. This is always fixed, which means that when we convert them to moles, that ratio is fixed also. Because the ratio of moles is the reason why definite proportions works. So we got 83.65 and divide that by 12.01. And we got 6.97. 6.97 moles of carbon. 16.35 and 1.01, we get 16.2 or 19 moles. Okay. That ratio is fixed, but it's not a whole number. So remember, in math, if you do the same thing, if you multiply or divide by the same value for both of them, then the ratio is still fixed. So what we can do is divide through by the smallest one. That's going to be equal to 1. And this is going to be equal to about 2.3. 32. Okay, it's about a third. And at this point now, we're trying to get close to whole numbers. So we don't have to be a stickler about exact values. In order to get rid of that third, because we have to have whole numbers, if we multiply by 3, that's 3 times 2 is 6, plus 3 times 0.3 is 1. So 1 plus 6 is 7. Our empirical formula would be C3H7. Okay, we're continuing. There we go. Okay, 16.22. Let me see if I calculated this one correctly. 16.35, enter 1.01. No, I said 16.19. Oh, I see. They're using more decimal places for the hydrogen. That's okay. All right. So now if we multiply by 3, we get the empirical ratio of 3 to 7. Okay. So how would we go from this one to the molecular formula? Well, we need another piece of information that we don't have yet. We need to know the molar mass of the actual compound. Because if we calculate the mass for a mole of this formula, we would get 3 times 12.01 plus 7 times 1.07. Excuse me, 1.01. And that would be equal to 43.10 grams per mole of the empirical. What I call the empirical weight, the EW. So now, knowing this, if we are given the molar mass at 86.2 grams per mole, so the true molecular weight is 86.2 grams per mole. Okay. Notice that if we multiply this one times, if n equals 1, then our molecular weight is 43. That's not it. If n equals 2, then 2 times this, C6H14, 2 times this is about 86. So that means that n has to be equal to 2 to give us this molecular weight, this molar mass. Now that was an explanation why, but as a practical matter, if you're given a problem with percent composition and you get to this point, then you're given this value for the actual molar mass. All you have to do is calculate the empirical weight and ratio the two. 86.2 divided by 43.1 equals 2. There's your n. That's your multiplier. Okay. C6H14, that's hexane. Okay, let's see how much time we got. I've got 20 minutes left. And Okay. Just this last two slides, work on this problem, so we can work this problem out in the time remaining. Let's see. No, I don't need this. Now, as usual, there are handouts. I have PowerPoint slide handouts. I have a review document, and I have worked problems. I have a key for the review document, and I have worked problems that you would get hard copies in class, or if you go to Brightspace in the module for EXAM3, you'll find those resources. The only way you're going to get good at working these problems is to work as many as you can out of that review document and do your homework. You need to practice, practice, practice. If you don't, if you try to just run through one of them and say, I got it, I guarantee you don't got it. You need to practice. So let's see what we have. 49.3% carbon. Carbon. 6.9% hydrogen. And this is by mass. 43.8% oxygen. So assume 100 grams, 100 gram sample. With a 100 gram sample, you have 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Now we can convert grams to moles. Carbon is going to be 12.01 grams per mole. Hydrogen is 1.01. And oxygen is 16. All right, we'll do a quick calculation. 49.3 divided by 12.01 is 4.10 moles. And 6.9 divided by 1.01 is 6.83 moles. And then 43.8 divided by 16 is 2.74. Okay. So now we need to reduce these to find the whole number ratio. This is a fixed ratio, but we need to divide everything through by 274. Notice the smallest number is where we start, because this one is going to be 1. 6.83 is going to be about 2.5. And 4.1 entered about 2.74 is 1.5. And we're getting closer. How do you get rid of a half? What do you mean to multiply? Multiply by 2. Each one multiplied by 2 maintains the original molar ratio. This is 3, this is 5, this is 2. So the empirical formula is carbon 3, hydrogen 5, and oxygen 2. We need to know what is N. Well, the first question is, what's the empirical formula? We found that. We'll go through the steps. Here we go. 3, 5, and 2. Then if we're given the actual molar mass of the compound is 146. So what's the empirical weight for this one? It's 3 times 12.01 plus 5 times 1.01 plus 2 times 16 for oxygen. Okay. And you should be able to knock that out pretty quick. Times 3, and then 5.05 plus, and then 32 plus 7308. 73.08 grams per mole. And we're given the actual value is 146. Divided by 73.08 is 2. Closest whole number, and it's very close, is 2. So this is equal to 2, and our formula is C6H10O4 for adipic acid. Adipic acid is a fatty acid, right? Everybody's got them in their body. Some people have too much. There we go. So there's our ratio, gives us our multiplier, and there's our molecular formula. And that's it. Okay. Well, since there's nobody here except me, we're done. And what we'll have for, let me check this off. Check this on. Next Tuesday, this is Thursday, so next week, next Tuesday, we'll have a review. So you've got plenty of time to work as many of those problems as you can. And if you choose, Zoom into class or come to class in person and tell me which ones you had trouble with. We'll work those. If nobody shows up, then I'll take the review document and I'll pick some of them out and work them on the board to give you a feel for each one of the types of problems that you may encounter on the exam. But that's the end of it. We're done for today. And exam 2 is due by midnight tonight, which is February 13th, 2025.